Today, we're going to talk about one of the most incredible stories of modern history. It's about how a machine that once filled an entire room, literally, shrank down to fit in our pockets, and in doing so, it completely rewired our world.
I mean, seriously, just to wrap your head around the scale of this whole thing, imagine for a second that the phone in your hand or the laptop you're watching this on was the size of a school bus. It's a crazy thought, right? But honestly, that's not too far from where we started. The journey from that to this is it's absolutely wild.
And just look at this contrast right here. On one side, you've got the ENIAC, one of the very first electronic computers from back in 1946. We're talking 1,800 square feet. It ran on 18,000 super fragile glass vacuum tubes, and it could crank out about 5,000 calculations a second. Pretty impressive for its time. But on the other side, a smartphone. Millions of tiny transistors doing billions of operations every single second. It is an almost unimaginable leap in power and an absolutely incredible shrinking act.
So, how in the world did this even happen? Well, it all starts with understanding what a computer actually is. The name itself comes from to compute, which means to calculate. But if you only see it as a calculator, you're missing the very thing that makes it so revolutionary.
See, the real magic of a computer is that it's a data processor. And data isn't just numbers. It's everything. It's passenger info for a train booking. It's complex variables and a huge scientific problem. The computer takes in all this raw data, sorts it, merges it, and transforms it into useful, organized information. It's not just solving math problems, it's solving information problems.
So what is it about these data processors that's so revolutionary? Well, they have this unique set of characteristics, you could almost call them superpowers, that set them apart from any tool humanity had ever built before.
Just think about this combination. First, you've got incredible speed, billions of calculations a second. Then there's perfect accuracy. It does exactly what it's told every single time. It has diligence. It never gets tired. It never gets bored. It just keeps going. It has versatility to tackle pretty much any logical task you can throw at it. And it has a flawless memory for insane amounts of data. It's not any single one of these things, but all of them working together, that makes the computer so ridiculously powerful.
But, and this is a big but, there's a crucial catch to all that accuracy. It's captured perfectly by the old programmer's phrase, garbage in, garbage out. A computer is incredibly precise, sure, but it has zero common sense. It only works with what you give it. So if you feed it bad data or flawed instructions, you will get a perfectly calculated but completely wrong answer.
All right, so with those fundamentals in mind, let's take a journey back, way back to where this all began. The age of giant, room-sized machines.
The need for fast, accurate calculation is centuries old. It started with clunky mechanical calculators back in the 1600s. But the real conceptual breakthrough, the big idea, came from Charles Babbage in the 19th century. His analytical engine was the first design for a general-purpose programmable computer. It was way too complex to build back then, but his ideas basically laid the groundwork for machines like the Mark I in 1944.
And that brings us right back to the giant ENIAC. This was the first all-electronic computer built for the military. I mean, try to picture a machine that takes up a 20 by 40-foot room. To change its program, you didn't type code on a keyboard. Nope. You had people physically rewiring massive boards. It was basically a piece of architecture as much as it was a machine.
So, how did we get from that behemoth to the devices we have today? Well, the whole journey unfolds across 5 distinct technological leaps, what we call generations. So let's start with leap number 1, which is all defined by a single game-changing piece of hardware. The first generation was the era of the vacuum tube. These were these delicate glass bulbs that could act as super high-speed electronic switches. They were the key piece of tech that made machines like ENIAC even possible, letting them perform calculations in milliseconds.
But, oh man, the trade-offs were enormous. On one hand, they were the fastest things on Earth, but they were also massive. They generated a ton of heat, they sucked up huge amounts of power, and they were incredibly unreliable because those vacuum tubes failed constantly. They were absolutely groundbreaking, but they were also deeply, deeply impractical.
The second generation was sparked by a revolutionary invention that came out of Bell Labs, the transistor. This tiny solid-state device could do everything a vacuum tube could, but it did it without the fragile glass, the intense heat, or the filament. It was a complete game changer. And the impact was immediate. Second-gen computers were about 10 times faster, way smaller, much more reliable, and used far less power. And this is the moment computing really started to spread out, moving from government labs into the business world for things like payroll and inventory. They were still big, don't get me wrong, but they were finally becoming practical tools.
Okay, so the next great leap was the integrated circuit, or the IC. Instead of painstakingly wiring individual transistors together by hand, engineers figured out how to basically etch an entire circuit, transistors, resistors, all of it, onto a single tiny piece of silicon. This was a revolution in how you build these things.
Now, these early ICs, using what was called small-scale integration, could fit maybe 10 to 20 components on a single chip. That might not sound like much now, but just think about it. Eliminating the need to hand-wire all those tiny parts was a massive step forward in making computers smaller, cheaper, and way more reliable.
And the result? Computers got drastically smaller and faster. Again. This era gave us the mini-computer, which made computing affordable for smaller organizations. And it gave us time-sharing operating systems, which let multiple people use one machine at the same time, a huge boost for productivity.
The fourth generation, while this delivered what was arguably the biggest leap of them all, the microprocessor. For the very first time, engineers could fit the entire brain of a computer, all its arithmetic, logic, and control units, onto a single integrated circuit. This was truly a computer on a chip.
And this led to just explosive exponential growth. Thanks to a technique called Very Large-Scale Integration, or VLSI, engineers could suddenly pack over 1 million components onto a single chip. This wasn't just a small improvement. This was a complete paradigm shift.
And what did the microprocessor give us? It gave us the personal computer. Suddenly, computers were small enough, cheap enough, and reliable enough to sit on a desk, in an office, or even in a home. They didn't need special air conditioning anymore. This era also gave us computer networks and graphical user interfaces, making computers accessible to pretty much everyone.
And that brings us to the fifth and current generation, which kicked off around 1989. This era is really defined by two huge things. Ultra-large-scale integration, we're talking tens of millions of components on a chip, and the explosion of global connectivity.
The power of ULSI gave us laptops, portable computing, and the ability to handle complex multimedia. But the real defining feature of this generation is the network. The internet and the World Wide Web connected all these powerful devices, and that fundamentally changed how we communicate, work, learn, well, how we live.
So there you have it. We went from these room-sized giants that had to be painstakingly wired by hand to these globally connected supercomputers that we just carry around in our pockets. In just a few decades, our entire world has been, well, it's been reprogrammed. I mean, just think about it. We watched a machine go from the size of a room to the size of a wallet, all within a single human lifetime. The pace of this change is it's breathtaking. So the real question is, what on earth happens in the next one?